Yeah. Hey, hello everyone for the second day of the summer school, where we have Marc starting with the following lecture on symmetries.
All right, so hi everyone, welcome back. I hope everyone is well rested and ready for the second half of the lecture. I also hope that yesterday was understandable and that there are not too many questions. Hopefully today we can give some examples and make things a bit more explicit, so you understand more concretely and more precise examples what we did yesterday. So just to summarize extremely briefly, because we will do this again, we just summarized yesterday the results about Noether's theorem for symmetries in mechanical systems and then field theory very quickly. And then we explained what happens when we try to generalize to gauge field theories. And what we saw, the crucial thing to remember for this lecture, the main message is that in gauge theories, the non-trivial essential information about the symmetries is encoded on lower dimensional manifolds, namely codimension 2 boundaries. So by codimension 2, in 4-dimensional spacetime, this would be a 2-dimensional sphere boundary. And what we also saw is that this is not simply the analogous of the Noether charge in mechanics or field theory, which we call Q, but there can be an additional contribution. And this is summarized in this little boxed formula, which we derived for general relativity, for gravity. And now we want to understand what is precisely the meaning of this formula, how we can apply it, and what is the meaning of this, possible non-integrable contribution, which is responsible for the fact that we have a slashed variation, delta slash, on the left-hand side. So to do this, I would like to go very step by step through the example of 3-dimensional gravity, because many things can be understood and made very precise in 3-dimensional gravity. And then if we have this in mind, it's kind of easier to understand what happens in the more complicated 4-dimensional case. So for this, luckily Maite did already a little review of 3D gravity yesterday in what we call first order variables, so connection and triad variables. What I want to do here is use kind of useful and powerful index-free notations. So this is the reason for this is that essentially when working with first order variables, connection and a triad, we are essentially manipulating Lie algebra valued differential forms. So because of this, you have a bunch of indices to carry if you want to be very explicit, because there are the Lie algebra indices and also the form indices. So if we make everything explicit, it becomes very heavy, and it's not the most efficient way to work in a sense. So because of this, I would like to use some index-free notation, and throughout this whole chapter, do everything as much as possible without indices. For this, we just have to be a bit comfortable manipulating these Lie algebra valued forms. So the first thing we need to know is that we have two variables. The first one is a gauge connection, omega, it's a 1 form. And the second one is a triad, which we call E. And the connection has a curvature, field strength, which is denoted by F. And this is the formula. And there is also a torsion, which is computed as the covariant derivative of the triad E. Now, in these formulas, we should just remember that there are implicit internal indices everywhere. In fact, these implicit internal indices, they are just indices that we'll make them explicit a bit later when we need to compute things explicitly. But you should just remember that whenever you have two Lie algebra valued forms, they are implicitly paired with an internal Lorentzian metric. So we will do everything in the Lorentzian case here. And this bracket, which I write in many places, is just the Lie algebra commutator. So we have the wedge product between forms and the Lie algebra commutator between Lie algebra valued forms. And if I make this E wedge bracket of E wedge E completely explicit, you see that we have the form indices which appear with the antisymmetric epsilon tensor, the 3-form D3x, and an epsilon tensor for the Lie algebra indices, which comes from the commutator. So if we just keep this in mind, in principle, we can do all of our computations. So first order gravity is just another way to rewrite the Einstein-Hilbert Lagrangian. This will lead to subtleties, which we will see in a minute. But for the moment, we just use different variables to write basically the same theory, which is Einstein General Relativity. So for the moment, let me set the prefactors to 1. So kappa, which is 8 pi g, I set it to 1. We will reintroduce it a bit later. And the Einstein-Hilbert-Lagrangian, which we studied yesterday, please note that I just shifted the cosmological constant by a factor of 2 for convenience, but this is completely innocent. So r minus 4 lambda. In first order variables, this is just E wedge f, and the cosmological term is E wedge E. So this is EC is the Einstein-Cartan-Lagrangian. Now to study this theory, we can apply the recipe which we already outlined yesterday. Namely, we have a Lagrangian, and yesterday we mentioned this master variational formula. And this formula was telling us that whenever we have a Lagrangian, we can put its variation in the form of the equations of motion times the variations of the fields, plus a boundary term, which identifies the symplectic potential. So if we do this explicitly with the Einstein-Cartan-Lagrangian, we see that we identify delta of omega, wedge the torsion, the omega of E, plus delta of E, wedge a curvature term, f minus lambda E wedge E. And of course, we get the boundary term, which identifies the symplectic potential theta. And so we know now, if we're getting used to this, that these boundary terms, so the symplectic potential, we get it from integrating by parts the derivatives in the Lagrangian. If you look at the Einstein-Cartan-Lagrangian, the only place where the derivative appears is in the field strength F. So it's kind of obvious that the potential will be of the form delta omega wedge E, if we stare a bit at this formula. Now, just to tell you once again the meaning of these equations of motion, here we say that we are in a first order formulation because there are two independent variables, and we get two first order equations of motion, as opposed to usual metric formulation of general relativity, where we get a single second order equation of motion. So the way to connect this first order formulation with the second order formulation is just to solve the torsion equation. So the torsion equation tells us that we can express the connection as a function of E, or as a function of the metric. And again, we will do this explicitly in a few slides. We will explicitly compute this torsion-free connection. And then when we plug this first equation of motion into the curvature equation of motion, this curvature reduces to the familiar Riemannian Ricci curvature equation, which is here the Einstein equation, r mu nu equals 4 lambda g mu nu. Now, just as a reminder also, Maite mentioned this yesterday, I just want to remind you that three-dimensional gravity is has the peculiar property that it's a topological theory, meaning that it has no local degrees of freedom. It has no gravitons, no gravitational waves. A way to see this is to just count the number of phase space degrees of freedom. So to count the number of degrees of freedom in the phase space form, for example, we have to count the number of independent phase space variables, and you have to subtract the first class constraints. And as Maite also recalled yesterday, we have to subtract the first class constraints twice because they also generate gauge transformations. And if we do this counting here, on the spatial slice, we have 6 connection components, 6 triad components, but you have 3 flatness constraints and 3 torsion constraints. So the counting tells us that there are 0 phase space degrees of freedom. If you did this counting in 4-dimensional general relativity, instead of 0, you would find 4, namely the 2 polarizations of the graviton plus the 2 conjugate momenta. Now, just as a word of caution at this point, I just mentioned, I don't know why I mentioned this here, I could have done it later, but I just want to say that we are going to start to work with the symplectic potential. We have to be a bit careful when we work with differential forms about where the components actually are and what we do with these objects. Because these forms, we are free to pull them back on various lower dimensional manifolds. So for example, if I pull back the symplectic potential on a time-lag boundary, so spanned by coordinates, let's say a time t and an angle phi, you see the symplectic potential delta omega wedge E in components picks up the t and the phi components of omega and E. But on the other hand, if I'm interested in computing the symplectic structure, which as we saw yesterday, involves the integrating the symplectic current on a spatial, on a space-like hypersurface, If we do this, we pick different components of the symplectic potential because we write the pullback on a different hypersurface in a different manifold, and this picks up the R and phi components. So you see, these are different objects because we evaluate them at different locations. So we will have to keep this in mind. So now, of course, we want to discuss the symmetries of this theory because this is a lecture about symmetries in general relativity. Now it just happens that this theory has so different sets of symmetries, which we want to discuss now. So the first one is what we call simply Lorentz transformations. So these Lorentz transformations, they transform the internal Lie algebra indices of the triad E and of the connection omega. And with this compact index-free notation, Lorentz transformation on E is just a commutator. So the rotation of E by the Lie algebra element alpha. And a Lorentz transformation acting on omega is just a covariant derivative. This is like this transformation of omega is like for a non-abelian gauge field in Yang-Mills theory. Now, as I think Maite also mentioned yesterday, three-dimensional gravity is also invariant under so-called translations. So maybe the word is a bit misleading, which is why I put translations between quotations. This will become a bit more explicit later when we remove the cosmological constant. But by extension, usually we call these symmetries translations in any case. And so these translations, they act on E by a covariant derivative, as shown here, and they act on omega by a rotation of E. And you see that the cosmological constant is involved in this formula. Now we can be very explicit and check explicitly that these are symmetries of this connection and triad first order formulation of 3D gravity. Well, to be explicit, we just, by brute force calculation, we compute this. So we take back our variational formula. This is what we had on the previous slide, relating the variation of the Lagrangian to variation of the fields and equations of motion and the symplectic potential on the boundary. And then you see in red, I plug the Lorentz transformation for omega. In orange, I plug the Lorentz transformation for the triad. And then I simplify these expressions by doing integration by parts. In purple, we use the useful fact that the squared of the covariant derivative gives essentially the field strength. So this is the purple term. And at the end of the day, manipulating this, you can convince yourself as an exercise that this is indeed vanishing. Now we can do the same thing for the translations, doing the same manipulation exactly. We will get that the transformation of the Lagrangian leaves us only with a boundary term. So that indeed, this is a symmetry of the theory. Also notice while passing that by doing this, we proved, or we checked on these two examples of these two symmetries, Noether's second theorem in the case of Lorentz transformations and translations. So the second theorem, as we said yesterday, is a theorem telling us that the piece of the variation of the Lagrangian, which involves the equations of motion and the variation of the fields, when evaluated on a gauge transformation, this is off-shell a boundary term. You see that in the case of translations, this is a bit analogous to what we did in metric general relativity yesterday. This is true because it involves this Bianchi identity, which is saying that the covariant derivative of the field strength is identically vanishing. Okay, so we just checked that these two transformations are symmetries very well. Now we are interested in computing the algebra of these transformations.
Marc?
Yes?
There's a question for you to ask a bit more the clarification, to clarify the notation in the first line. Of
the very first line here?
I don't know. Yes.
Okay. So alpha here is a Lie algebra valued scalar, a zero form. And so as expected, you see I'm acting on E, and I get again a one form, because on the right, the only one form is E, and alpha is a zero form. And the bracket just means that it's just a Lie algebra commutator between E seen as a Lie algebra element and alpha seen as a Lie algebra element. So in explicit indices, with what we have on the first slide here, see the commutator, the bracket is just an epsilon. So here, if I put back the indices, if I make them explicit, E on the left-hand side has a Lie algebra index and has a form index. On the right, the form index hasn't moved. It's again on E, but the Lie algebra indices on the right, you should read this as epsilon ijk ej alpha k. Right. And same thing for the transformation of the connection on the right. Yeah, sorry, I don't have anything to. No, alpha is a 0 form. I see in the chat that someone is asking. Alpha is a 0 form, otherwise this wouldn't be consistent, because on the left I would have a 1 form, and on the right I would have a 2 form. And also notice that I'm putting a comma and not a wedge product, because alpha is a 0 form, so I cannot wedge E with alpha. Okay. More questions. The last step of equation 1. The last step of the Lorentz transformation. Yes, sorry, I didn't make this explicit. So you see that when I use the master, this variational formula, I really invite you to also check this. Since we are evaluating the variations to be gauge transformations, we have the symplectic potential, and we also have to evaluate the symplectic potential on a gauge transformation, which is what I denoted by theta with the gauge transformation delta alpha. And now if we just take the symplectic potential that we had on the previous slide, so delta omega wedge E, we take delta to be a gauge transformation delta alpha, and then you will see that this boundary term identically cancels. So that's the last step of the calculation here. So now we want to look at the algebra of these transformations to see if it already tells us something interesting about the structure of the symmetries of this theory. So notice that for the moment we didn't talk about the charges or anything. We're just looking at the transformations as transformations acting on the fields and on the Lagrangian. And only later on we will move to the charges. So what we can do, of course, is pick a field. Say you take the triad E or the connection. You can act successively with 2 transformations, and then you can commute the 2 transformations. So by doing so, you're just computing essentially the commutator of these 2 transformations. But if you do this, you will find commutation relations, which are given here. So the first bracket is telling you that if you commute a Lorentz transformation J with parameter alpha and a translation with parameter phi, you get again a translation whose parameter is the Lie algebra bracket of alpha and phi. If you commute 2 Lorentz transformations, you get a Lorentz transformation. And if you commute 2 translations, you get up to the cosmological constant, a Lorentz transformation. Well, it turns out that this algebraic structure is something which we can recognize. It's something which has actually a meaning and a geometrical meaning and a name, because this just coincides with the isometry algebra of the constant curvature spacetime. So to explain this, we have to, I didn't mention this on the previous slide, but since in fact 3-dimensional gravity is topological, all the solutions of 3-dimensional gravity, they locally look exactly the same, and they only differ by the sign of the cosmological constant. So if the cosmological constant is 0, all solutions look locally like Minkowski space. If the cosmological constant is positive, all solutions look locally like de Sitter space. And if lambda is negative, all the solutions locally look like anti-de Sitter space. So the only freedom that you have in 3-dimensional gravity is to take these local patches of constant curvature spacetimes and glue them with non-trivial topology. This is how you can construct non-trivial solutions of 3-dimensional gravity. But locally, the structure is always the same and uniquely determined by the cosmological constants. So now these constant curvature spacetimes, whether it is Minkowski space in the flat case, de Sitter space or anti-de Sitter space, they have isometry groups, and these groups have an algebra. So we can talk about the isometry algebra of these constant curvature spacetimes. And these brackets which you see here are precisely the brackets of the isometry algebra of these constant curvature spacetimes. So more precisely, if you are in Lorentzian signature, which we do here, in the 0 cosmological constant case, the isometry algebra of Minkowski space is just the 2 + 1 dimensional Poincaré algebra, so ISO 2-1. If the cosmological constant is negative, the isometry algebra of anti-de Sitter space is the conformal algebra SO22. And if the cosmological constant is positive, the isometry algebra of the zeta space is the Lorentz algebra SO31. You can repeat the same game if you are in Euclidean signature for your space-time. And then in the flat case, you will have ISO3, so the Euclidean 3D Poincaré algebra. For negative lambda, you will have the Lorentz algebra. And if you're in Euclidean signature with positive cosmological constants, that's the only case where you get actually a compact group of isometries, and this is SO4. And you will probably see in Maite's lecture on spin forms that this case where the group is compact plays actually a special role in the construction of spin form models, precisely because now the gauge group is compact. But let's forget this for the moment. So now, of course, we talked about Lorentz transformations and translations, but this is a gravitational theory, and we are really interested in diffeomorphisms. So what I want to explain here a bit is the relationship that the diffeomorphisms have with the Lorentz transformations and the translations in three-dimensional gravity. So diffeomorphisms, I think Maite also mentioned this yesterday, and now we can prove it with this kind of efficient index-free notation. We just want to prove here that the diffeomorphisms, they are not independent symmetries from the Lorentz transformations and the translations. And in fact, the diffeomorphisms, which act by the Lie derivative via Cartan's magic formula, which we saw yesterday, you can rewrite them on shell. So when the equations of motion hold, as gauge transformations, so Lorentz transformations and translations, which have field-dependent parameters of transformations. And this will be the crucial thing to understand. So this is the proof of this statement in the case of a diffeomorphism acting on the triad and acting on the connection. So if you look at the first proof acting on the triad, the first equality is just the Cartan formula. And then the second equality, you see that I replace the ordinary exterior derivative by a covariant derivative. This is at the expense of introducing the last term, which is this commutator. And if you massage a bit this second equality, you can show essentially that this is a Lorentz transformation delta J plus a translation delta T with field-dependent parameters, plus the equations of motion, so the vector xi contracted with the torsion equation. And it's completely analogous in the case of a diffeomorphism acting on the connection. You do a bit the same manipulation, and you get exactly the same result. So now just at this point, you could wonder how this is consistent with actually the transformation of the Lagrangian, because now you could wonder what happens if you actually act with this formula for the diffeomorphisms. So instead of acting with the first line, namely the usual formula for the Lie derivative, what happens if you act with the third line in every transformation here? What happens to this when you act on the Lagrangian? How do you show that the Lagrangian is diffeomorphism invariant if you act with the third line instead of acting with the first line? Well, this actually works. It's completely consistent because it's a general result that in a theory, the equations of motion always act as trivial symmetries. So if you take the master variational formula that we had, I invite you to check that if you use the last line, so of this expression for the diffeomorphisms, so so the line involving the equation of motion, well, we already showed that the Lorentz transformations and the translations are symmetries of the Lagrangian. So delta J and delta T, they both annihilate variations of the Lagrangian. But what I invite you to check is that the last term in orange, which is proportional to the equations of motion, when you replace this, when you take this as a transformation of the fields in the Lagrangian, you also get 0. This is just a statement that the equations of motion, they act as trivial symmetries. So now we want to, now that we know the symmetries of the theory, we want to be more specific and do what we mentioned yesterday. We want to compute the charges and the algebra of the charges and see what the information, what kind of information is encoded in the algebra of charges. So to do this, what I suggest is that we look more closely at the Lorentz transformations and do everything explicitly step by step. So first of all, we can compute explicitly the symplectic structure. So the symplectic structure is very easy to compute. By the way, notice that you see here at this point an advantage of the first order formulation, working with the connection omega and the triad E. because the symplectic potential is just delta omega wedge E. It's a much simpler expression than what we had yesterday in the case of a metric gravity. So it's a much simpler expression than the symplectic potential expressed in terms of the metric tensor G. So because of this, the symplectic structure is very simple, and it's just delta omega wedge delta E. Also notice that here I made explicit the fact that when I act with a variation delta on the symplectic potential, I pick up a minus sign just because these field variations are Grassmannians. So when a variation is going through another variation, we pick up a minus sign. This is the same rule as for, again, the exterior derivative in space-time. So now that we have the symplectic structure, we can do what we mentioned yesterday. We can explicitly contract one of the variations of the symplectic structure with a gauge transformation. So take one of these arbitrary field variations to be a specific gauge transformation, namely a Lorentz transformation, and see what this gives us. So if we do this, so this is explicitly in the second equality. So you see, I take the symplectic structure and I replace the variations, keeping in mind that these variations are anti-symmetrized. I replace the first one on omega with the gauge transformation delta alpha minus, and then I replace the second one on E with the gauge transformation delta alpha of E. Then I use the explicit formula for these gauge transformations, delta alpha, and I get the third equality. And then by just manipulating this, you can show that this is a total variation delta. So it's a total variation delta of d omega alpha wedge E. So we just showed here in the case of Lorentz transformations that in this case, the generator of these gauge transformations is actually integrable, because immediately we obtain the variation delta in front of the expression under the integral. So we can pull the variation out and really give a meaning to the generator J of alpha. So now this generator, which as we just said is integrable in this case, is given by what? Well, to see what it's given by, you see in this calculation we obtained a bulk integral over the slice sigma in the bulk of the space-time. But if we just integrate this by parts, so I take this covariant derivative and I integrate by parts, I produce a boundary term in orange, and we also produce a bulk term. This now is exactly the formula which we showed yesterday. If you remember yesterday, we showed that generically, for any gauge theory, any gauge transformation, if we contract a gauge transformation with the symplectic structure, we get a bulk integral over sigma, which vanishes on shell. And this piece which vanishes on shell is the constraint in Dirac's Hamiltonian language, or the off-shell piece of Nutter's second theorem, the off-shell piece of the Nutter current, which is given by the second theorem. This is the red piece here. And then there is always a boundary piece, which survives when we go on shell. And this is what, by sometimes abuse of language, we just call the charge here. So now again, this is what we said yesterday. We notice here what the covariant phase space gives us. It tells us precisely the fact that the generator of these Lorentz gauge transformations is not the smeared Gauss constraint. The smeared Gauss constraint, which you would see as the constraint in the Hamiltonian analysis of Dirac, is the bulk integral, which is in red. But this object is not functionally differentiable, as we argued yesterday. The object which is functionally differentiable differs from this smeared Gauss constraint by a boundary term, which is precisely the charge of the transformation. Now we can also check explicitly the other thing which we mentioned yesterday, namely that by construction of the covariant phase space, once we have this integrable generator, by construction, this is such that when acting by Poisson bracket on the field, this generates precisely the gauge transformation that we started with. So you see, this is the explicit expression computation. I compute the Poisson bracket between E and the generator J of alpha. This, of course, involves functional integrals and functional derivatives of the generator J alpha. And when I compute these Poisson brackets, if you're very kind of careful with the integrals and the delta functions, we get that this is just the commutator of E and alpha. So this is completely consistent. You just notice, in fact, that if you have in mind what we usually do in the Dirac Hamiltonian analysis, this is a bit going in the opposite direction. Usually in the Hamiltonian analysis à la Dirac, we start with the Lagrangian of the theory, we put it in Hamiltonian form, then we identify the constraints, and then we ask, okay, which transformations on phase space, which symmetries are these first-class constraints generating? And we compute the Poisson brackets, and we read the symmetries that the constraints are generating. Here with the covariant phase space, we ask the question the other way around, in fact. We start with the form of the transformation, so we know how the transformation is acting on the fields. This is just delta alpha. This is what the knowledge that we started with. And then we feed this to the symplectic structure. We give this to the symplectic structure, and the symplectic structure spits out for us, gives us the generator of this transformation. So it's going a bit in a sense, you can think that this goes in the opposite direction. Here we just check that the loop is complete and everything is consistent and fits in nicely. Okay, so now that we have the charge of the Lorentz transformations, we can compute the full charge algebra between Lorentz transformations and translations. So from now on, just for convenience, let's just go on shell once and for all and drop these weak equalities, because I don't want to keep track of them and then forget them and then create confusion. I will just assume that we are on shell. So whenever I write J alpha and T alpha, I really write the boundary piece. So I really write the charge, which is this surface integral. So we just showed that the charge for Lorentz transformation, so curly J of alpha, is this integral of alpha E. If you repeat the same computation as on the previous slide for the translations, you will see that the charge for translations is the integral over the one-dimensional boundary of phi times omega. Now, if you compute the algebra of these, sorry, let me remove this. To compute the algebra of these gauge transformations, so the algebra of these charges, what we saw yesterday is that to compute this Poisson algebra, we can just contract the symplectic structure twice with two variations. So if we contract the symplectic structure once, we get the generator. And if we contract the symplectic structure twice, we get the Poisson bracket between two generators corresponding to the two variations. If we do this explicitly, well, we will find the following result. We will find, so we also mentioned this briefly yesterday. Here we have a concrete example of this. We mentioned that if the charges of a theory are integrable, then there is a representation theorem, which we didn't prove, but essentially the theorem tells us that the algebra of the Poisson bracket of the charges reproduces the algebra of the symmetry parameters up to possible central extensions. And here we see exactly this happening. So you see the first bracket is just telling us that the Poisson bracket of two Lorentz transformations is again a Lorentz transformation, completely consistent with the Lorentz algebra. What is more unusual here is that you see the second bracket has an extra term on the right-hand side. It has a sort of an anomalous term. And this is precisely what we call a central term, a central extension. Why central? Because you can see that this term does not depend on the fields of the theory. So because it doesn't depend on the fields, it commutes with any other generator you can think of, because there is no field dependency. So if you act with a variation on this boundary term alpha d phi, the variation will not see this term. So this term commutes with everyone. That's why we call it central. And by the way, in gray here, I have put the very short proof of how this term is produced. We can ask ourselves what is the mechanism that actually produces this term? What's the reason why this term appears? And you can see here that this is completely inevitable because, so by definition, the Poisson bracket of J and alpha with T, of J alpha with T phi is the transformation, so the translation delta T phi, acting on the generator J alpha. So to do this, I go back to the generator J alpha, which is up there, and I act on this with a translation. The translation acts on the triad E by producing here the covariant derivative, d omega of phi, and then I just separate the ordinary derivative and the commutator. This commutator term here produces this translation with the bracket, and I'm left with this piece, alpha d phi, which doesn't go anywhere. I cannot get rid of this piece. I cannot match it with anything else. It just stays there. And it stays there, and it's completely fine, because this piece is precisely an allowed piece in this algebra, namely a central extension. So why this piece is allowed in the algebra? Because in fact, this algebra here is a bit of a has a different nature than the algebra which we encountered earlier. This is what I wrote in bold here. This algebra is in fact infinite dimensional, and sometimes, usually we call this a current algebra. Yeah, I think that's usually the terminology for this. So this is an infinite dimensional Lie algebra called the current algebra. And the reason why this is infinite dimensional is that it's allowed to depend. You see that it's defined with arbitrary Lie algebra zero forms, which are the smearing functions of the charges. So alpha and phi in these charges are Lie algebra valued functions, but they can be any Lie algebra valued function that you want. And because of this, this algebra is infinite dimensional. So you see also that this bracket, if you look at it, so this algebra, of course, mimics exactly the algebra which we called G lambda and that we found a few slides ago. When we computed the commutation relations of the Lorentz transformations and the translations, but without using the charges, just seen as transformations acting on the fields, we found the algebra G lambda, which was the isometry algebra of these constant curvature spacetimes. Here we just showed that the charge algebra reproduces the same structure as this global algebra, but now it's an infinite dimensional extension of this global algebra. So this is what I wrote here, that the algebra G lambda, which we had before, you can think of it as the global part of this infinite dimensional current algebra. Namely, it's the part of the algebra where you take the generators alpha and phi to be constants. So if you do this, you see that the central term drops because alpha d phi becomes 0. And you're only left for each generator with 3 possibilities, because you only have 3 generators of Lorentz transformations and 3 generators of translations in 3 dimensions. Now the last thing, and again, we will see in a minute another kind of example of this mechanism, that we take an algebra of parameters. Later on, we will take an algebra of vector fields and then compute the corresponding algebra of charges and see again that the algebra of charges is a central extension of the algebra of the vector fields. Now, the last thing we can do explicitly, just to kind of manipulate this and convince ourselves that it works, is that these charges, they're actually conserved on shell. So one way to check conservation of, for example, the Lorentz charge is to actually use the fact that the time evolution is given to us by the total Hamiltonian. If we had done the Hamiltonian analysis of this system, we would have found that the total Hamiltonian given to us by Dirac is precisely the Lorentz generator, but with a smearing parameter, which is the time component of the connection. This is the Lagrange multiplier of corresponding to the connection. And plus a translation whose smearing parameter is the time component of the triad field. So if I take this as my total Hamiltonian, now I know how the total Hamiltonian acts on a Lorentz transformation or a translation, because I have these Poisson brackets, which we just computed. So if I compute the variation of the Lorentz generator, I just have to keep track of the fact, you see the first term here accounts for the variation of the gauge parameter, because it can be an arbitrary function of space and time. And then I have the Poisson bracket between the total Hamiltonian and the Lorentz charge J alpha. Now, if you use the brackets above, you will find the last equality here, that this reduces to this surface integral. And essentially, staring a bit at this, we can convince ourselves that this is essentially the T phi component of the torsion equation of motion. So because of this, on shell, we get that this Lorentz charge is conserved. And again, in the case of diffeomorphisms, in a minute, we will see again examples of these conserved charges and have explicitly check the conservation of the charges which we compute.
Marc?
Yes?
There is a question about central extension.
Yes.
Ali is asking that you are saying that the extension is anomalous, and he wanted to know in what sense, when there is an H bar, does it show up in the extended term in an interesting way?
Yes, thanks for the question. Maybe, in fact, I spoke too fast. I didn't mean to say that so the central extension is not anomalous by itself. It's allowed. What I just wanted to say is that if we compute this bracket, it's not what we, if we had never encountered this, we would not be happy with this bracket, because we would see a term in the second bracket on the right-hand side, precisely the central term, which is not, again, a generator. So we have the impression that this algebra doesn't close, in fact. And in a sense, this algebra does not close, in fact, because of this central term. But it's an acceptable non-closure of the algebra, precisely because this term is central. And the other thing with respect to the H bar comment that we have to keep in mind is that this is a particular type of central extension, because it's what we usually call a classical central extension. Namely, it's coming completely from a classical computation. It doesn't come from ordering ambiguities or H bar factors, or which is how quantum central charges can be produced. And we will see again a bit later that what the role of these classical central charges, what their role can be, especially in ADS space. Okay, so now if we move to diffeomorphisms. So we just showed, so of course what we're interested in is, I just in fact showed the, let me mention one last thing on this slide here. I really encourage you to explicitly prove this form for the translation charges, because if you remember a few slides ago, we showed that when we act with a translation on the Lagrangian, we produce a boundary term. So that's, of course, it's a symmetry of the theory, but the Lorentz transformations, when you act on the Lagrangian, they don't produce a boundary term. Whereas the translations, they produce a boundary term. So in this case, they're a bit analogous to the diffeomorphisms. We showed yesterday that if you act by Lie derivative on a Lagrangian, so as a diffeomorphism, this produces a boundary term. And this is essentially the reason for which, when we computed the formula for the charge, we had this extra contribution in addition to the standard Noether contribution to the charge. So now, in fact, we have covered implicitly, without saying it, basically all cases that can happen. For the Lorentz transformation, you can actually show that this charge alpha E on the boundary is identically exactly the Noether charge. For Lorentz transformations, there is no difference between the Hamiltonian charge and the Noether charge. For the translations, you can actually show that this piece phi omega, which is the charge, is not the Noether charge. If you compute the Noether charge, you will get something else. And there is secretly here, but because everything is consistent, so we implicitly use this equation. Here, this Noether piece has already been combined in the case of the translations with the piece produced by the boundary term, by the boundary term coming from the variation of the Lagrangian. So in the case of diffeomorphisms, and we will again prove this in the next slide, we show that there is a contribution which may not be integrable, and we have to worry about integrability of this contribution. But in the case of translations, this contribution is here, but it's always integrable. So in the case of Lorentz transformations, this contribution is not here, and the Hamiltonian charge is the Noether charge. In the case of translations, this contribution is here, but it's integrable. So you have no integrability problem, but the Hamiltonian charge is not the Noether charge, because this piece is secretly here. And in the case of diffeomorphisms, as we saw, this piece is here, and we have to discuss its integrability. So this is what we do exactly now. So we can wonder how this matches with what we discussed earlier. Well, before we actually showed that in 3D gravity, at least, in fact, this is, I also should mention that this is just because the theory is topological. It is because the theory is topological that you can trade the diffeomorphisms for internal gauge transformations, like the Lorentz transformations and the translations. So we just showed before that the diffeomorphisms, you can realize them on shell as field-dependent Lorentz transformations and translations. But now this is interesting because now for the first time, we are discussing transformations with gauge parameters which depend on the fields. And so far, it seems that our formalism is not really able to handle this because we said it a bit yesterday. We were always careful to assume that the parameters don't depend on the fields. So they are not acted on by the field variations. So now if they depend on the fields, you see, we have this equality here between an infinitesimal diffeomorphism and an infinitesimal Lorentz transformation and translation. We want to ask, can we promote this equality to an equality between the charges of the theory? So not between the transformations, this we already showed, but to an equality between the charges. And precisely if we want to do this, because this involves now parameters which are field dependent, we have to be very careful. So just to be careful, it's actually easy to be careful and to do it the proper way. We just have to reintroduce this delta slash notation. So this means that the diffeomorphism generator, which we want to compute, so delta slash of D on the left, you see on the right, I write it as a Lorentz charge with a field-dependent parameter, psi omega, plus a translation with a field-dependent parameter, psi contracted with E. And I put a delta slash because we know that this Lorentz transformation and this translation, they are not integrable because the parameter is field dependent. Now explicitly, we can massage this and see what this gives us. So I'm writing explicitly the step. You see the first line, I just make explicit the charge of the Lorentz transformation with the field dependent parameter psi omega. So this is psi contracted with omega times delta E. So you see, if you just look at this red piece, that this is manifestly not integrable. I cannot pull the delta in front of this because the omega is in the way. So I cannot do this. And same thing for the translation, the orange piece. So yeah, I cannot put the delta out because the E is in the way. But now, however, you can a bit just massage this. You can just rewrite this, this formula. You see in the second equality, the first term, I didn't touch it. I left it unchanged. I just removed the color. And the orange term, what I did is, I don't know how you call this. It's not an integration by parts. It's interior product by parts, I guess. Because I put the interior product on E, I put it back on as the interior product of delta omega wedge E. And then I'm writing the interior product on delta omega. So I'm just using this basic rule of the interior product acting on the two form, delta omega wedge E. And now by doing so, what appeared nicely is completely consistent with what we said yesterday. We have computed the diffeomorphism charge from the Lorentz transformation and the translation with field-dependent parameters. And this has produced for us this non-integrable psi theta piece. See, this was just produced by our calculation. So this is completely consistent with what we said yesterday in the case of diffeomorphisms. Now, the only thing which I didn't write explicitly is a delta Q. So now we know from what we showed yesterday that Q is now in principle the neuter charge in the first order connection triad formulation. So the diffeomorphism neuter charge written in terms of omega and E. The only thing, again, which we have to be careful here, which is why I used a peculiar notation, is that you see, I wrote delta Q and I put the psi outside of delta Q. So I mean the variation delta Q evaluated on the vector psi. So this is indeed, as I just said, of the form delta Q minus psi theta, which is what we showed yesterday should hold in the case of diffeomorphisms. Where this Q, what is this Q? Well, this Q is precisely the Noether charge for three-dimensional Einstein-Cartan gravity. So in metric formulation yesterday, we derived the metric Noether charge, which is the Komar charge. Now we just derived the first order analog of the Komar charge, namely psi omega times E. Now the only thing which this notation is taking into account is that, well, we have also to be careful, and we want to be a bit more general now. It will be important later, because now we have to account for possible field dependency of the vector field itself. You see, at the beginning of this example, we were extremely careful about what happens if the parameters of the Lorentz transformation and the translation depend on the fields. And by being careful about this, we produced this psi theta piece of the diffeomorphism charge. Now, to be very general, and because we will need it very soon, we have to also be careful about the possibility that the vector field itself, for which you evaluate a diffeomorphism charge, can itself depend on the field content of the theory. And because of this, this is why I use the notation delta Q evaluated on psi. And you see, I'm just using this, this formula. I'm saying that delta Q evaluated on psi, this is the same as the variation acting on. So you see, after the equality, delta of Q of psi, here I mean, with this notation, I'm implicitly assuming that delta hits on the vector field as well. So because of this, I'm subtracting the charge evaluating on the variation of the vector field. So you see that if the vector field is field independent, delta psi is 0, and this notation doesn't change anything, right? I can use any notation, there is no ambiguity. All I'm saying here is that if the vector field is allowed to be field dependent, which is the most general case, whenever you write expressions such that the variation of a charge, so here the variation of the Noether charge, you just have to choose a notation. You have to be very careful about whether you want your variations to act on the vector field or not. So this is just what we want to keep track of in this case.
Marc?
Yes.
There is an interesting question. Someone is asking that if the action principle is well posed, the pullback of theta to the boundary should on shell be equal to the variation of the boundary Lagrangian. Is that enough to ensure integrability here?
No, it's not enough to ensure, thanks for the question. It's never enough to ensure integrability, precisely because of something which I mentioned in the beginning. I said that we have to be careful about the components of theta. So indeed, so far we didn't mention the variational principle, because you will see that in fact we secretly don't need it. I will come back to this in a minute. But as you mentioned, the variational principle, so you take the action, you want to make the action functionally differentiable, and for this you have to get rid of a boundary term, which is essentially the integral of theta on, let's say, a time-like boundary. But the time-like boundary, for example, has components, coordinates t and phi, the time and the angle phi around the boundary. These components are restricted by the variational principle, that's true. But here what is important to notice is that the contraction psi with theta picks up, this contraction sees other components of the symplectic potential theta. And these other components of the symplectic potential theta, they are not constrained by the variational principle. So therefore, the variational principle is not enough to guarantee that this piece is integrable. I hope this answers the question. In fact, it's an important question, so I hope it answers it. And we will see, in fact, in examples in a minute. I think I even write it now that why this is really important. Otherwise, of course, we could think, oh, now we just have the potential on the boundary, but on the boundary, the potential is restricted by the variational principle, so we can get rid of this term. Well, that's not the case, again, because if the vector field psi is general, so here it's a three-dimensional vector field, if it probes all three dimensions, it will probe all the components of the symplectic potential. And some of the components of the symplectic potential, they just do whatever they want. They're not constrained by the variational principle. So now precisely, how can we actually now achieve integrability of these charges? What happens? What is a specific example where you can make sense, you can give a concrete meaning to an integrable charge? Well, the first kind of thing we can do, which is a bit a restriction, but you see that it works. There is a particular case. That's the case for which the vector field is just tangent. By tangent, I mean that, so here we're in 3 dimensions. So the vector field has 3 directions. Say I imagine that my spacetime is a filled cylinder. So I pick coordinates t, r, and phi. Phi is the coordinate along the one-dimensional boundary S on which we have defined these charges. Well, you can restrict yourself to, you can imagine that you have a vector field which is tangent, which is only on the phi direction. This means that the vector field does not move this boundary S. It only rotates the boundary, but it doesn't move it in the radial direction, and it doesn't translate the boundary in time. Well, if you have such a vector field, you can just look at, again, now we have to be careful about which components of this differential form we are picking up. So it's psi contracted with theta, but this is evaluated on the codimension 1 boundary S. So theta is a 2 form. So you see it has always 2 indices. And first, so in these 2 indices, it's anti-symmetric because it's a 2 form. And the vector field psi is contracted with the t component, then with the r component. But you see that the phi component doesn't show up because if the phi component is psi phi contracted with theta phi phi. But theta phi phi is 0 because theta is a 2 form. So this just means that this contraction evaluated on the boundary, so psi contracted with theta evaluated on the boundary is insensitive to the angular part of the vector field. It only depends on psi t and psi r. So therefore, if the vector field is tangent, this piece is identically vanishing, right? So if this piece is identically vanishing, then the charge is trivially integrable, right? So that's one way that you can produce a charge which is always integrable, namely you restrict yourself to a tangent vector field. Of course, this is not so useful because eventually we want to look at vector fields which move in the time direction because we want to compute the mass or the energy. So we want to look precisely at the case which is not this purely tangential case. But luckily, this still works because in particular examples, what it can be that the boundary conditions are such that, so the field content of the theory is such that this piece is actually integrable. And please, I don't want this to conflict with what I said earlier. I'm saying boundary conditions on the dynamical fields. I don't mean boundary condition in the sense just variational principle, because as we just argued, variational principle is not strictly speaking enough. By boundary condition, I just mean the type of theory you're working with. Here, we did not specify what type of metrics we were looking at, what type of solutions, and what type of vector fields we were looking at. But these two things go hand in hand, and it can very well be that for certain spacetimes, so for certain metrics and certain vector fields, isometries, this piece is non-zero, but is integrable. This can be the case. And we will see that in many interesting examples, this is actually the case. But this we have to do step by step. And just to finish on this slide, I want to mention that in the case where the vector field is tangent, if you could ask yourself, what is the algebra of these diffeomorphism charges? Well, now you have a one-dimensional diffeomorphism of the circle. If you compute the algebra, of course, you get what you expect, namely the algebra of diffeomorphisms. And this sometimes this is known as the Witt algebra of circle diffeomorphisms. And maybe we can have a 2-minute break at this point, if it's useful.
Sure. If someone has a question, it might be the best time to ask it. Or not, we can all take 1 minute to.
So just trying to see if I can finish. Hal is asking about the central charge. I think for the interpretation of the central charge, I think we have to be careful about its dimensionality and the couplings. So at least we will see soon that there are, in 3D gravity, depending on the boundary conditions, there are two types of central charges, at least that I know of. And they are a bit on a different footing because one of them you can freely rescale it because it just depends on Newton's coupling. So in this sense, it's not as physical as the other, the Virasoro central charge. So maybe the example that you mentioned is a case where you cannot reabsorb or redefine the value of the central charge. And I think if you cannot redefine the value of the central charge, then probably it acquires a special physical meaning. But I'm not sure in generality what happens in 3D gravity, if there is a known kind of classification of the possible cases. Okay, maybe we can, I think Christophe is back.
Yeah, let's start again.
Okay, we can start again. So just to mention now something which I will just gloss very quickly over this, but I want to mention it because maybe you have encountered this or you will encounter it at some point. And it's something interesting. And it's just a short relationship with a conformal field theory. This is just to mention the fact that what we just did now, it has actually a special meaning in some textbooks. This is known as the Sugawara construction. And the Sugawara construction is actually a way to obtain a diffeomorphism algebra from a Lie algebra. And this construction is precisely what is called in conformal field theory, the Sugawara construction. Because if you think about it, this expression here told us that we obtained the diffeomorphism charge, which then has a diffeomorphism algebra, from charges which are charges of a Lie algebra, of an infinite dimensional current Lie algebra. So out of a Lie algebra, a current algebra, we're producing a diffeomorphism algebra, an algebra of vector fields. And this construction is what we call Sugawara construction. To see this algebraically, at least, so I want to say that this has a very important and meaning and definition in conformal field theory and also mathematically. I just want to explain just very basically algebraically that this is essentially what we did. You can easily see this in Fourier modes, in fact. So I'm just taking the generator of the Lorentz charge, and I'm expanding this on Fourier modes over the circle S. So now N, so I is the Lie algebra index, and N are the Fourier modes. And then I'm rewriting, for example, one of the brackets. You can rewrite all the brackets, but I'm writing here the bracket between a Lorentz transformation and a translation. Now what we can do in fact, we already saw something. We already saw that when we go from just the algebra of the gauge parameters to the algebra of the charges, there is an infinite dimensional extension of the algebra. We go from just the global, in this case, it was a 6-dimensional algebra, to an infinite dimensional algebra, which we call the current algebra. Now, when you have such a current algebra, you are free to do yet another extension, which is to consider what we call the universal enveloping algebra of this current algebra. This means that you allow yourself to consider arbitrary polynomials of generators of this algebra. And in particular, it turns out that there is a particular quadratic generator that you can build from the current algebra. So now we take the current algebra, which is generated by the Lorentz generators J and the translation generators T, and we do a non-trivial operation. We construct a quadratic generator by pairing together via this infinite sum over the modes, a Lorentz generator and a translation generator. Well, if you call this quadratic generator D, well, there's a reason why we call it D, because now you can check that the algebra of these generators D is precisely the Fourier mode representation of the diffeomorphism generator, which satisfies again this Witt algebra of diffeomorphisms of the circle, which is written here in terms of Fourier modes. So this is in fact intimately related to the fact that that secretly underlying this I don't know, in fact, what underlies what, but in fact, there's a relationship between these algebras of boundary charges and the fact that in three-dimensional gravity, there are conformal field theories living on the boundary and knowing about these charges and knowing about these charge algebras. Okay, so this is just if you encounter this one day, you know at least where it comes from in 3D gravity. So now we can do a physical example, kind of physical application, and use this to compute something. Well, to do this, there is something interesting to do in 3D, which is to look at the three-dimensional black hole. So the three-dimensional black hole is called the Btz Black Hole. This is named after Baniados, Teitelbaum, and Zanelli, who discovered this solution in '92. And I also give credit to Steve Carlip, who studied this very extensively. So this is a solution of three-dimensional gravity. It can actually be either Lorentzian or Euclidean. I do the Lorentzian case here. But what you need is that the cosmological constant be negative. So in fact, previously, secretly, I already had chosen the signs of lambda to be such that lambda negative is ADS. Sometimes people use a different convention, just have to be a bit careful. So here I want the spacetime to be ADS. So I want lambda to be negative. So usually it's convenient to say that lambda is minus 1 over L squared. So this is negative. Then I consider the following line elements. So I'm using coordinates tr and phi. And in this line element, you see I'm specifying two things. There's an angular dependent piece here, which has an angular momentum j, or at least you will see that this has interpretation of an angular momentum. And the lapse function squared here is given by this expression. There is a mass term, r squared over L squared, so cosmological constant term, and again, this angular momentum piece. Well, it turns out that this defines a black hole in three-dimensional gravity. So as we said, three-dimensional gravity, it can look as like a trivial system because it has no local degrees of freedom, it has no gravitons. Locally, all solutions look the same, but the solutions can have globally non-trivial properties. This is precisely how you can build these black hole solutions. And in fact, they have a very, at least in these coordinates, they have a very simple metric. You can see that this metric has coefficients which don't depend on t and phi. So you already know that there will be killing vectors dt and d phi. We want to go back to them later. And so one thing that we should also mention is that because this is three-dimensional gravity, all the spacetimes have constant curvature. So these black hole solutions, they are not black holes like in the four-dimensional case, which have a curvature singularity. So they don't have a curvature singularity, but they have an horizon, as one can explicitly check. And interestingly, these horizons have thermodynamic properties, which is why people have used these 3D black holes to get insights into the physics of 4D black holes. So the horizons, we get them by looking at the zeros of the lapse function. We see that there are two horizons, an outer one and an inner one, because we can have a non-zero angular momentum J. Now we can write the mass and the angular momentum in terms of these two radii, r plus and r minus. If you want, you can explicitly check that there is an outer event horizon, which is killing, and it's generated by the vector field dt and omega h times d phi, where omega h is this factor here involving the outer radius and the angular momentum. You can check that on the horizon r plus, this vector is null, and that this vector is horizon forming. K here, sorry, kappa is the surface gravity, and simple arguments of black hole thermodynamics, which I think you will review in the lecture by Alejandro, which starts tomorrow, where this comes from, if you're not familiar with this. But hopefully in Alejandro's lecture, you can kind of keep this example of the Btz black hole in mind, and also try to apply what he says to this three-dimensional black hole. This is just to say that this black hole has nice thermodynamic properties, just like in 4D. In particular, it satisfies the first law of black hole mechanics, and it has a Bekenstein-Hawking entropy. And the entropy, as expected, is given by the area divided by 4G, except that now we're in 2+1 dimensional spacetime. So the area, so it's not a sphere, it's a circle. So the area is the perimeter. So instead of the area, you have 2 pi times the radius. In fact, So secretly, what we have written here is a family of solutions. And this family of solutions, you can organize them in this nice phase diagram, which I took from a paper by Barnish, Gomberov, and Gonzalez. And this is just showing you that there is, in fact, some rich structure even in three-dimensional gravity. Namely, you have this kind of phase space of solutions. So see when the mass is -1/8 times g, you have pure ADS3. Then if the mass is a bit higher, you have what we call conical defects. If it's lower, you have conical excesses. And when the mass is positive, you have these Btz black holes. And whenever you're outside of a boundary defined by the constraint j equals m times L, you have naked singularities and closed time-like curves. What we want to do with these black holes is just compute the charge, because in fact, we're not really interested in all the detailed physics and thermodynamics of these black holes. What we want to understand is how to use this charge formula that we derived to compute physical quantities. So we want to compute the charge. Also, I'm using this as a kind of an opportunity to show how we compute this if we use first order connection and triad variables, because it's something that we don't always do explicitly. So it's nice to do it on an example. And again, it's always simpler in 3D than in 4D. So if you were to compute the charge, the first thing you would do is pick an internal metric. So let's say that we pick, so our spacetime is Lorentzian, so the internal metric has to be Lorentzian. We had coordinates tr phi, so let's choose the internal metric to be diagonal, -1, 1, 1. And now you just have to pick a triad. So the triad is just a 3x3 matrix, which is compatible with this metric in the sense that the metric tensor G mu nu has to be EI mu, EJ nu, contracted with the internal metric. Of course, I'm saying pick a triad compatible because you can pick infinitely many triads because they can always differ by a Lorentz transformation. Because the metric is a Lorentz invariant quantity, you can always define the triad that you want to pick up to a Lorentz transformation. So I think the simple one to pick is this one. So it's just this simple 3x3 matrix with 4 non-vanishing entries. Now you want to compute the compatible torsionless connection. Because of course I have to specify at some point. You see, I said earlier that the potential, the symplectic potential is easier when expressed in terms of connection and triad variables, because it's just delta omega wedge E. But since in this formalism you're always on shell, secretly if you want to apply these formulas, well, you have to write omega as a function of E. Omega is not something which on shell is independent. Omega is only specified by E. So on shell, what is the expression for omega? Well, to see this, you just have to look at the torsion equation. You see the torsion equation, so you look at the covariant derivative of the triad field E. But now, since E is a hybrid object, it has Lie algebra indices and spacetime indices. The covariant derivative acts on the spacetime indices. This is why I have the usual Riemannian covariant derivative here. And then there is a connection piece, which is transforming the internal index with a rotation, epsilon ijk. Now you can just convince yourself that you can invert this formula to get omega as a function of E. And the inversion formula is just what I wrote here on the right. So this is the explicit definition of the torsionless compatible connection in 3D gravity. So you see that once you know the triad and the metric, you know everything explicitly, you can compute this. And again, it's a 3x3 matrix. If you compute it in the case of the Btz black hole, you will find this result. So in principle, we could check this as an exercise. Now what we want to check is take the formula which we had for the charge and apply it to the case of the Btz black hole. So for this, to apply it to a specific case, well, we have to give two things to the charge. We have to specify a metric. This we did by specifying here the triad, and also we derive the connection. And you also have to specify the vector field for which you want to actually compute the charge. So here there are two natural vector fields for which we can compute the charge, namely the Killing vector fields of the space-time. So the dt vector field and the d phi vector field. If you do this, you use the charge formula that we had earlier. You look now at vector fields, look at isometries psi t and psi phi. And then the charge which you will get is just measuring the mass and the angular momentum of this Btz black hole. here I have reintroduced the couplings just to show that in principle you get, I mean, of course you can rescale M, but I wanted to show here that once you properly fix the couplings and the units, what you call the mass in the metric is what is measured by the charge. There's no factor of G or something, a factor of pi, everything matches. So the 1/8 pi G is the coupling of the Lagrangian, which I reintroduced. The 4G in the charge is just coming from the charge calculation. It will produce this factor of 4G. And there is a factor of 2 pi coming from the circle integral. And together, this gives you just psi t times m minus psi phi times j. So as expected, we see that time translations give us the mass of the system or the energy, and rotations give us the angular momentum. Okay, so now that we have done this simple example, we have to now go really to where things become more interesting. And these are, so this is the topic of asymptotic symmetries. So now so far we understood that when we have gauge symmetries, we have now a formula to compute charges associated with diffeomorphisms. We gave an example of this, and we computed physical quantities measured by these charges. In this case, the mass and the angular momentum of these Btz black holes. Now there is a topic which is the focus of a lot of recent work, very important and interesting work, and this has to do with asymptotic symmetries. So I want to explain a bit briefly what is this topic and what happens. Again, we are here only in 3-dimensional case. This will really be interesting when we go to 4D, but I want to take 3D as an example to set the ideas. So schematically, what we want to do, we'll make this more precise in the next chapter, is we are interested in studying families of metrics of a particular form. We want to say that the metrics are, for example, something that you have probably heard is asymptotically flat metrics. So we want to consider metrics which are specified by some kind of background, like a flat metric, but allow for deviations, controlled deviations from these flat metrics. So schematically, I write this as a metric, which is G background plus subleading corrections. Of course, if I want to make this explicit, we have to pick coordinates, we have to pick boundary conditions, we have to really specify the form of the metrics, and we have to be a bit more precise about what we mean by asymptotic, when we say asymptotic symmetries, and what I mean by subleading in this equation, which is here. Subleading in which sense, in which when which coordinate is large. So this is what we have to specify. What we also want to do is that we want to see if at least we can pick a family of metrics, if we can actually give a meaning to this equation here, such that the phase space that we're writing down contains physically interesting solutions. If you write a phase space which contains trivial solutions or no interesting solutions, well then we can use it, but it won't really tell us anything interesting. So of course, in 4 dimensions, what we have in mind is to describe a large enough class of asymptotically flat spacetimes in which you can measure asymptotically far from an event, the radiation, for example, produced by some phenomenon, like the collision between 2 black holes, for example. So you want your spacetime your phase space to contain these complicated solutions with interesting physics inside. So now, again, a bit schematically for the moment, what we typically call the group G of asymptotic symmetries is the group of gauge transformations which preserve the boundary conditions, modded out by the group of trivial gauge transformations. Because as we have shown, when we have, for example, a diffeomorphism invariant theory, there can be diffeomorphisms to which we can assign a non-zero charge. But there are also diffeomorphisms which are trivial, which give a vanishing charge. So these diffeomorphisms which are trivial, we can kind of intuitively think that we want to kind of remove them. We want to only extract the charge corresponding to diffeomorphisms which preserve the boundary conditions and which are non-vanishing charges. We will see in the next slide what we mean by diffeomorphism preserving the boundary conditions. So again, as a warm-up to the 4-dimensional case, we want to do just this in 3D and consider 3-dimensional asymptotic symmetries. And what is kind of peculiar but nice at the same time is that since 3-dimensional gravity is topological, we can actually in 3D get exact results even at finite distance. So you can a bit forget this notion of asymptotically or subleading because everything is completely exact at every order. So now just to mention, because maybe you see where we're trying to go. So historically, initially, this was first studied in 3D gravity by Brown and Eno in a famous paper in 1986. And they studied the case which was 3D anti-de Sitter space, so ADS3, in a special gauge for the metric, in a special family of metrics, which we call the Pfefferman-Graham gauge. We could reproduce this calculation, but actually, in order to fit more kind of, I don't want to say modern because Pfefferman-Graham is of course still heavily used, but more notation which you usually find in the 4-dimensional asymptotically flat case, we will use here in 3D what we call the Bondi gauge. And then that's the opportunity to introduce this Bondi gauge and see a bit how it works. And then hopefully when you encounter this in 4 dimensions, probably in the talk by Strominger and Nichols next week, this will speak to you. So to do this, to set up Bondi gauge, we have to talk a bit about coordinates first. Well, first, what I want to do is consider null coordinates. So these null coordinates are just the usual retarded or advanced time coordinates. Here I take u to be t minus r, and I have a radial coordinate and an angular coordinate phi. And in these coordinates, 3D Minkowski spacetime is just the familiar rewriting of this line element. So the first one is in Cartesian coordinates. Then we have polar coordinates. And then we have the null coordinates. So which sometimes we call, or I mean here, at least in this case, later on, we will call a version of this Bondi gauge or Bondi coordinates. Now I just want to write a space-time diagram to explain a bit what happens in these coordinates and to see where a different structure lives. So sorry, I should have flashed the diagram a bit later. Please forget about it first. I just want to say that, of course, this pure Minkowski spacetime has exact Killing vectors, which are the Poincaré transformations of 3D Minkowski spacetime. So isometries of 3D Minkowski spacetime. So these exact Killing vectors are generated by, so it's a 6-parameter family. So these are Poincaré transformations, which are sum of spacetime Lorentz transformations and spacetime translations. So now I put this diagram here to just show what happens in these null coordinates. So in these null coordinates, we have, so the old time t is flowing upwards. Then in the null coordinates, so r equals 0 is at the center here. At 45-degree angles, we have here in green, the u equals constant lines. So these are directions along which radiation goes. So null geodesics. So of course, here we're in 3D, so there is no radiation, but I still draw in red here the radiation, which is eventually what we want to describe in 4 dimensions. When you go now along a constant u direction to r to infinity, you reach, you see this upper line here, which we call future null infinity, denoted scri plus. So future null infinity has the topology of r times a d minus 2-dimensional sphere. And this d minus 2-dimensional sphere, we call it the celestial sphere. So in 3-dimensional gravity, this is a celestial circle. It's only 1-dimensional. So it's parameterized by the angle phi. And also on scri plus, so at each point of scri plus parameterized by u, you have such a celestial circle or such a celestial sphere. And then here up there, you have time-like infinity, a little I plus. Here you have space-like infinity, I naught. And here we have past null infinity. Okay, so this was just to set up a bit what a space-time diagram can look like in these coordinates. And essentially, we're interested in extracting information which reaches future null infinity, because this is eventually where radiation will reach us. This is why we're interested in families of spacetimes, which are asymptotically flat, in the sense that at future net infinity, when R goes to infinity, we recover something which looks like Minkowski spacetime, but regardless of what happens, I mean, not regardless, because we want to, of course, in the subleading terms, we want to read information about the physical processes which took place inside of the bulk. And the physics inside of the bulk can be messy and complicated and very nonlinear. But the beauty of this kind of rewriting of Einstein equations using this notion of asymptotically flat spacetimes is that when we are far away from this region where extremely nonlinear and complicated phenomena happen, when we're sufficiently far away, we can read nice, nice information and nice data, nice physical information. What we want to see here is what kind of physical information we can actually construct and extract. And of course, this will involve computing charges associated with some transformations. So the way this works in 3 dimensions, to set this up, well, what we said is that we have to specify a solution space or a phase space for the theory. And here we will also write what we call on-shell metrics. So the first thing to do is to pick, again, these null coordinates and to gauge fix the metric. I will explain a bit later on today or maybe next Monday how we get this gauge fixed form of the metric. But essentially, you can think of this as using diffeomorphism freedom to pick 3 coordinates and put the metric in this form. Typically, we call this form of the metric the Bondi-Sachs form of the metric. So see, this is the so this is not the Minkowski metric in Bondi null coordinates, because here we have a function beta, a function v, and we have a function u here. Now we have to specify what v, beta, and u can be. This is precisely specified for us by looking at Einstein equations. So the Einstein equations, if you go ahead and try to solve them now, they tell you what the fall-offs of these fields should be like. Essentially, they tell you that v over r can be of order 0 in R, minus lambda, the cosmological constant, times r squared. U can be of order -2, and beta can be of order -1. So you see that, for example, at r goes to infinity, this contains, depending on the sign of this cosmological constant lambda, it contains Minkowski space or ADS3 or DS3. But importantly, notice that these spacetimes, it contains this, for example, Minkowski, but is not globally diffeomorphic to Minkowski, precisely because the factor that's in front of du squared does not have to be -1. It can be anything. So it's something a bit more general. Now, because we are in 3D, it turns out that there is something kind of beautiful and magical, or at least very mathematically nice that happens, namely that we can exactly solve Einstein equations in this Bondi-Sachs gauge. So this expansion in 1 over r actually stops explicitly, and you can show that in this Bondi gauge, the most general exact solution to Einstein equations, so here they take the form, so r mu nu plus 2 lambda g mu nu equals 0, you can check that the form of the solution to the Einstein equations in this Bondi gauge take this form which is given here. So I invite you to check this, and maybe I said that I think on Monday the idea was to do the last lecture on some very simple numerical methods to actually have a simple code that actually computes these charges. So with this code, we can explicitly show that this is an exact solution. If you want, you can also check this by hand. Now you see that this metric on shell is parameterized by 2 quantities. Suggestively, because of what happens in 4D, m is typically what we call the Bondi mass aspect, and n is traditionally called the angular momentum aspect. So the Bondi mass aspect is, of course, a scalar, and here we are in 3 dimensions, so the angular momentum aspect is also a scalar field. And notice that these functions m and n, they live they are parameterized by u and phi. They are independent of r. Now, if I just, for notational simplicity, I denote the angular derivative by prime. In fact, if you want to show that this metric in Bondi gauge is an exact solution is an exact solution of Einstein equations, you just have to impose two evolution equations. You can show that the U phi Einstein equation tells you that the U derivative of n is the angular derivative of m. So dun is m prime. And once you impose this, you can then show that the UU component of the Einstein equation tells you that dum is lambda n prime. So if you impose these two constraints, you solve Einstein equations. Now what we can do, I just tell you this not to confuse you, but just to, as a word of caution. Now you could ask yourself, okay, we didn't do this explicitly in the example of the Btz black hole, but we could have done the same. I don't know why I didn't do it before and only here, but you can ask yourself, what is the on-shell symplectic potential with this ansatz for solutions to Einstein equations? Well, if you did this, well, you can take, you can either even compute this in metric variables. You can take this metric here and use the metric expression for the symplectic potential, which we gave yesterday. Or you can define a triad E, then solve the torsion equation and define a connection omega, and then compute the potential delta omega wedge E with this exact solution in Bondi gauge. Well, if you did this, you would find that the potential has only a single non-vanishing component, and that this component is furthermore a total variation. From this, you would kind of conclude that there is no symplectic structure. But this is of course not true, because this is not how you compute, how you use the covariant phase space and how you compute the charges. In fact, you should not evaluate the symplectic potential on shell, because as you see here, if you evaluate the symplectic potential on shell, well, it completely trivializes. It's a total variation. So when you compute the symplectic current, which is the variation of the potential, you get delta squared of m, which is identically 0. This is just saying that to compute charges in the covariant phase space formalism, you cannot go on shell too quickly. You cannot go on shell at the beginning of the calculation. You first have to use the covariant formulas which we derived. And at the end of the calculation, once you have contracted the symplectic structure with the variations, then you can go on shell. This is a bit analogous to what happens if you wanted to study a theory and first you went on shell in the Lagrangian. If you go on shell in the Lagrangian, then typically things trivialize. So you should not go on shell too soon, in a sense. So just like you should not go on shell in the action or in the Lagrangian, you should not write the symplectic potential on shell. Yet this is still useful to compute if you want to just convince yourself that the on-shell variation of the action, if you fix the metric on the boundary, leads to a well-defined variational principle. Okay, so now that we have our family of metrics, so now we have a family of metrics parameterized by two functions of u and phi, namely the Bondi mass aspect m and the angular momentum aspect n. Now we can look at residual symmetries. So what we call residual symmetries? Well, these are vector fields, so generating diffeomorphisms, which preserve our boundary conditions, which preserve our family of on-shell metrics. Well, in which sense? In the sense that, well, we just wrote a family of on-shell metrics, G, which are functions of two arbitrary functions, m and n. Now we want to look at those diffeomorphisms such that the Lie derivative acting on this metric produces once again a metric in this family of metrics. So again, a metric G with new parameters. Maybe now the parameters have changed. They are allowed to change. And they are changing by, well, m becomes delta m and n becomes delta n. Now we ask ourselves, are there non-trivial diffeomorphisms? And what is the vector field generating them, which preserve the family of on-shell metrics precisely in this sense? This is just a question we can ask ourselves.
Marc,
yes?
You have 10 minutes left before questions.
Okay, this will be, okay. If we do go ahead and settle for this calculation, well, we find that you have to, in fact, specify two arbitrary functions, f and g. The only requirement is that these functions have to satisfy constraints a bit, you see, analogous to what m and n have to satisfy. The u derivative of f is related to g prime, and the u derivative of g is related to lambda f prime. With these two arbitrary functions, apart from this, these two functions are completely arbitrary. You find these AKVs, so this stands for asymptotic Killing vectors. These asymptotic Killing vectors, they take this form. There are vectors whose U component is F, the R component is given here, the phi component is given also here. Notice in particular that the R component depends on the fields now. There is an N dependency in here. So we are precisely in the case which we prepared ourselves for, namely to deal with diffeomorphisms whose parameter can depend on the fields. This is precisely what we encounter here. Now we want to ask exactly how the field transform under these diffeomorphisms. Well, if you look at the equation defining this preservation of the family of metrics, on the left-hand side, you compute the Lie derivative, and on the right-hand side here, you identify how the fields vary under these diffeomorphisms. If you do this, you will find that the parameters m and n vary in this way. Maybe this is not so suggestive at this point. We will see what this means, but to just jump ahead of ourselves, in fact, you can understand this either as the transformation law of the stress tensor of a conformal field theory. So in connection with a bit to what we said before, the fact that secretly there are underlying conformal field theory on the boundary here. Or in fact, another algebraic way to say this is that we don't know at this point because we don't know what the symmetry algebra is. But if we knew the symmetry algebra already, well, you could find that these fields, they transform as if they were in the coadjoint representation of the symmetry algebra. Now with an abuse of language, because it's not already really the case here, but we can call F super translations and G super rotations. And I will explain in a minute what this means. Okay, now I want to compute the algebra. So one thing you can do is what we did for 3D gravity earlier with Lorentz transformations and translations. We computed the algebra of the parameters themselves. Well, here we have vector fields, so we can compute the algebra of vector fields under the Lie bracket using the Lie derivative of vector fields. But now again, we have to be a bit careful because now the vector fields, they depend on the fields. So if we just compute, see the red piece here, which is just the Lie bracket, which is just one vector field acting on the other one by Lie derivative, you would not find that these vector fields form an algebra. You would not find that this closes. The reason for this is that the vector field has an R component, which is field dependent. Because of this, you have to correct the Lie bracket with this contribution here in orange. And you see that this contribution is precisely subtracting a piece, which is a diffeomorphism acting on the other one, but not acting by the Lie bracket, but acting in the sense that we wrote here. See, the radial piece has a field n inside, and when I act with another diffeomorphism, the diffeomorphism will hit the field n. So if you compute this modified bracket, which we sometimes denote by a star, you can find that this modified bracket closes. So two such asymptotic Killing vector fields, their modified bracket gives again an asymptotic Killing vector field. I'm not writing at this point explicitly what this psi on the right-hand side is, because this is telling us the algebra structure, because what I want to do is compute this in terms of charges. It will be a bit more explicit. And maybe if you have to stop, I can say one last thing. I just want to comment about these vector fields and what they generate, why we call them super translations and super rotations. So if you just think about flat Minkowski spacetime in the Bondi coordinates which we give earlier, well, flat Minkowski spacetime has exact Killing vectors, which are just Poincaré transformations. Poincaré transformations are parameterized by Lorentz transformations alpha and translations x. Sorry, I denoted here Lorentz transformations by x and translations by alpha. And in fact, of course, we know that flat Minkowski spacetime has only 6 such isometries. So 6 Lorentz transformations and translations. There are 3 Lorentz transformations in 3 dimensions and 3 translations in 3 directions. This means that these functions here, alpha of phi and x of phi, they're not arbitrary functions of phi. In fact, they have to satisfy a third order differential equation, meaning that when you write them, there are these 3 constants. And for example, the parameter alpha has to be of the form alpha 0, minus alpha 1 times the cos and alpha 2 times the sine. So it's not an arbitrary function. It has to be a constant or a cos or a sine. And the same thing for x. And these fixed functions means that there's only 6 isometries of Minkowski spacetime. Now, if you just rewrite a little bit the asymptotic Killing vector using the fact that these functions f and g satisfy these constraints. And sorry, I wrote it in the flat case here. So I'm taking lambda to 0. So on the previous slide, I'm taking the cosmological constant lambda to 0. And I'm taking this relationship between the u derivative and the angular derivative. And if I do this, you can essentially show that I'm rewriting here the asymptotic Killing vector. I'm just making explicit the phi, the angular piece, because I don't want to crowd the formula too much. But now you look at the angular piece, and you can compare this to the angular piece of the Killing vector of flat Minkowski spacetime. You see that it's functionally exactly the same thing. Now x has become y, and alpha has become t. And now the big difference is that in this case, y and t can be arbitrary functions on the circle. And because y and t can be arbitrary functions on the circle, this is why we have an infinite dimensional enhancement of the algebra of Lorentz transformations and translations. So these angle-dependent translations, T, we call them super translations, because they can be angle-dependent arbitrarily. So by the way, if we just go back, so a rigid time translation, so the Poincaré isometries, this corresponds to T being constant. And the rigid spatial translations, there are 2 of them, they correspond to the first spherical harmonics. And the super rotations, by analogy, they denote angle-dependent Lorentz transformations. So geometrically, what happens with these super translations is that they shift for you the u coordinate along scribe plus, but they can shift the u coordinate in a manner which depends arbitrarily on the angle. So you see, we can take this celestial circle here and deform it in a manner which depends arbitrarily on the angle phi, which is very different from what happens with the 6 Poincaré isometries. Now I wanted to compute the charges, but I guess
technically you have 2 minutes.
Maybe I can just, okay. Yeah, I wanted to mention a subtlety. So let me just show this. So I just want to say that now we can compute, apply the formula for the charges which we had earlier. If you apply the charge formula, I wanted to discuss a subtlety on this slide, but since we don't have time, let me not discuss the subtlety. The subtlety has to do with this 1/r piece. But just imagine that you are defining these charges asymptotically. So this 1/r piece isn't here. Well, it's a bit the same thing that happens in the case of the Btz black hole. The diffeomorphism charge will be, so f, the generator of super translation now, paired with this function m, and the generator of super rotation g, paired with the arbitrary function n. So f is paired with the Bondi mass aspect, and g is paired with the angular momentum aspect. Now, sorry, let me flash this. Now we can explicitly show that these charges are conserved using the Einstein equations. So the Einstein equation tells us how m and n evolve in time parameter u. If you use these relations here, which we stated earlier, you can show explicitly that the charge is conserved in time. Now what we said is that the representation theorem tells us that the algebra of these charges using covariant phase space should reflect the algebra which we found using this modified bracket, the bracket star, up to a possible central extension. We want to see whether this is the case. And if you just decompose the charge D as a sum of super rotations and super translations, I'm using the names J and P now, you will get this charge algebra. And I don't know, maybe I should stop here. Yeah, I mentioned maybe one last thing. Let me just mention this and then we can stop.
Okay.
And so I just want to mention that if you take the cosmological constant to be flat, to be 0, I'm just rewriting the algebra in terms of modes here, but this is what we call the centrally extended Bms3 algebra. So these vector fields generating super rotations and super translations, they give rise to charges, and these charges, they satisfy an infinite dimensional extension of the Poincaré algebra, which we call the Bms3 algebra. This is written here in terms of modes, and you see that potentially in this centrally extended Bms3 algebra, you can have two central extensions, C1 and C2. But what is important is that here you see in terms of the modes, you have a factor n squared minus 1. So for the modes which are given by n equals 0 plus minus 1, this central term is always 0. And these are precisely the 6 modes which correspond to the 6 Poincaré transformations. So these 6 modes, they are the Poincaré transformation spanning the global isometry algebra. And then the BMS algebra is an infinite dimensional extension of this, because in addition to Poincaré, you allow for arbitrarily angle-dependent translations and Lorentz transformations. And maybe I stop. Yeah, maybe I stop here.
Yeah, there are already a few questions.
Okay, yes.
So one by Dripto. I'm unmuting you if you want to ask your question.
Yeah, hello, am I audible?
Yeah.
Okay, so like I just wanted to quickly clarify what you meant by exact scaling vectors, which you mentioned in a few places. What exactly is it referring to by exact?
Did I say exact Killing vector?
Yeah, when you are presenting the diagram, the space-size diagram.
Here?
No, before, the first time.
This could be fine as well, but you mentioned it before.
I'm saying exact in the sense that they're not as opposed to asymptotic Killing vectors. So that they don't have to preserve the form of the metric asymptotically when R is large.
I see. Okay.
Which is what you would only require for asymptotic Killing vectors.
Okay, thank you.
So for asymptotic Killing vectors, you preserve some fall-offs. But for the usual notion of Killing vectors, you just identically annihilate the metric.
Yeah.
There is a second question on the Killing vector by Ongwei. Sorry, I think I butchered your name. You are on mute if you want to ask your question. You are not. It's not working. Well, he was asking if the Killing vector fields were at spatial like infinity or null infinity. Oh yeah, no, he's on mute.
Sorry, I have trouble in talking. I have trouble in speaking. Can you see the chat?
Okay, no problem. He was asking if the Killing vector field were at spatial like infinity or null infinity.
These are at null infinity, yes. Yes.
Okay, thank you.
Sure.
Are there any other questions?
Going up in the chat, I see.
Can either write it in the chat or raise your hand.
How do you see the hands?
No. And Marc, if you want to use your 9 remaining minutes to explain what you wanted to explain.
Why not? I mean, I can just, yeah, I think this we can skip. I mean, we had the algebra, so I just wanted to show. I mean, on Monday, the goal will be to explain the role of this BMS algebra in 4 dimensions. So BMS4. This was just to explain, to have a first encounter with this infinite dimensional extension of Poincaré, which is BMS3 in 3 dimensions. And the other thing which I wanted to mention is the reason to use these Bondi coordinates is that we can study at the same time the flat case when the cosmological constant is 0 and the DS or the ADS case. In particular, in the ADS case, if you take the cosmological constant to be negative, so I set again lambda to be 1 over L squared, we can just define these new diffeomorphism generators, D plus minus, as a combination of P and J. And then the algebra takes the famous Brown-Eno result, which is the form of a double Virasoro algebra. So Virasoro algebra is a central extension of the algebra of diffeomorphisms. So this D plus minus, you see that they form two commuting plus minus Virasoro algebras and plus and minus commute. And there is a central extension. So again, there are 6 zero modes corresponding to n equals 0, -1, and +1, where the central charge disappears. And these zero modes correspond to 6 conformal transformations, and they span the conformal algebra SO22, which is the isometry algebra of anti-de Sitter space. And the rest, the rest of the tower of the modes, they span the rest of the Virasoro algebra. And the central charge, when you write it in this form, is what we typically call the Brownlee central charge, and it's equal to 3L by 2G.
There are 2 questions in the chat, Marc.
Yeah.
One person is asking for any useful reference where he can go and be used to this formalism, because he is a bit new to this formalism.
Yes, in fact, I'm giving a bit more there, more references. I can flash them here. Yes, for example, here.
And there is a question on the Virasoro algebra. Someone is asking, is this Virasoro algebra is related to the ADS3 CFT2 in this case?
Yes, exactly. The Virasoro algebra is precisely related to ADS3 CFT2. In fact, this is how ADS3 CFT2 was discovered, in a sense, or a strong evidence for a gravitational realization of this. And in this case, the Brownlee central charge really has an interpretation as the central charge of a conformal field theory.
Do we still have questions? It seems not. So, well, let's thank Marc again for the lecture. And in half an hour, we will have Maïté Dupuis for the next lecture on LQG, spin foam, and spin networks. And during the coffee break, if you want, you can go to the Gather Town room if you want to continue discussing with people.
Thanks, everyone.